Hello and welcome to my presentation on the nested trees for longitudinal classification. In this study I will talk about the nested trees algorithm, which is a novel classification algorithm that's designed for longitudinal classification. It utilizes a unique model structure based on decision trees that I will show in just a bit. It is a classification algorithm, with classification of course being a subfield of data mining, which is the task of assigning class labels to data instances. We can train our classification models on pre-classified data, and we can use those classification models to later make predictions on newly found data. More specifically, we'll be working with longitudinal data. Longitudinal data is a type of data that contains repeated measurements of the same attributes, which are taken at different points in time. So we can measure these attributes repeatedly and then study their temporal patterns and make predictions about future events. This is an example of a longitudinal dataset that can be used for prediction of diabetes. It contains an ID for each patient, with 7 patients being in this dataset, and it contains 2 longitudinal attributes, the fasting glucose level and postprandial glucose level, both of them being measured at 4 different time points as represented by 4 attributes each. And we have a class variable called diabetes. So in the task of longitudinal classification, we would like to predict that diabetes label using these 2 longitudinal attributes that represent the fasting and postprandial glucose levels at different time points. Now, in the literature, there are a lot of studies that use longitudinal classification, and most of them use an approach called flattening. It is essentially an approach where you flatten the longitudinal dataset into a non-longitudinal dataset, meaning that the fasting glucose level at time point 3 and fasting glucose level at time point 4 would be considered as completely independent attributes, thus removing the longitudinal nature of the data. And this is the approach that most longitudinal studies use. Another type of approach is designing a custom algorithm. There are only a few studies that actually design custom algorithms that are aware of the longitudinal data, meaning that these 2 longitudinal attributes are analyzed by their models as being inseparable. So fasting glucose level, those 4 measurements there would be considered as a whole, and postprandial glucose levels would also be considered as a whole, not dividing them into 4 separate attributes. There are only a few such algorithms known in the literature, most of them using either support vector machines, random forest, or there's one interesting one using neural networks. And the main issue with all of those existing approaches is that they're scarcely interpretable. So the models are hard to interpret by end users. Interpretability, in this case, we're referring to understanding how our models make decisions. So we would prefer to have models that can be inspected directly or through some derived metrics that would give us some clarity on how decisions are being made. And in the context of longitudinal interpretability, we have additional questions to answer. So we are not only interested in how each class value is assigned, but we would also like to know how much does each longitudinal attribute affect classification, and we would like to know which longitudinal attributes are more useful than others. So when addressing this issue of interpretability, we can go to a conventional decision tree model. Decision trees are well-known classification models that can be very interpretable, since they have a simple structure that can be inspected manually. An end user can look at the decision tree and see exactly how each decision has been made. So as an example, if we have a tree that looks like this, predicting diabetes using that example dataset shown earlier, and we would like to see how this particular prediction was made, assigning the value yes to the diabetes column. We can track the path that was taken through the decision tree all the way to the leaf node that has assigned the diabetes value of yes. So decision trees are very interpretable like that. Now, when designing our novel classification algorithm, we would like an algorithm that uses longitudinal data, an algorithm that is based on decision trees, and an algorithm that has longitudinal interpretability. And an answer to all of those is a nested trees classification model. This classification model is based on the decision tree model, and it constructs a unique decision tree model that analyzes each longitudinal attribute as a whole. So let me show you what you mean. Here's an example of a nested trees model. In this model we have a big decision tree with some smaller decision trees embedded into the nodes of the bigger tree. So we have 3 longitudinal attributes, attribute 1, attribute 2, and attribute 3, analyzed by 3 different nodes. And inside each of those 3 nodes, we have inner decision trees that do that analysis for us. So let's look at the rightmost node, the one that concerns attribute 3. As you can see, it has an inner tree embedded into the node, which at the moment has 4 leaf nodes, and those 4 leaf nodes correspond to the 4 branches coming out of this bigger node. So effectively we have an embedded decision tree that makes those decisions for us and separates the training set into 4 subsets. Looking at the tree that's embedded into that node, we can see that this tree can look something like this, where 3 different temporal values of attribute 3 are being analyzed by different nodes, and those leaf nodes are being generated that later correspond to the branches of the outer node. So this nested tree models are being constructed in 2 levels. We have the outer level that constructs the bigger tree consisting of these large nodes, and we have the inner level which constructs those decision trees which are embedded into the nodes of the outer tree. So the outer process constructs the whole model, and the inner construction level constructs specifically those 3 embedded decision trees, which is why we call this algorithm nested trees. In the paper we have evaluated this algorithm against a more conventional binary decision tree algorithm, which has used the flattening approach instead of being longitudinally aware. We have used 10 classification problems to evaluate these 2 algorithms against each other, and we have analyzed predictive accuracy measures, sizes of the models, and we have made some comments on model interpretabilities as well. The data being used in the study is taken from the ELSA dataset, which is an English longitudinal study of aging, collecting various data for English population aged 50 and over, and we've used specifically the medical subsection of that dataset. In the results, we have noted that nested trees algorithm has outperformed the conventional decision trees that use the flattening approach instead of being longitudinally aware. Nested trees was more accurate overall, but has produced larger models. And interestingly enough, longitudinal attribute importance was in fact more apparent in the nested trees models, as commented in the results section. In the future, we are looking to develop this nested trees algorithm further. At the moment, we're testing features that make models smaller, make them more interpretable, and reduce construction time. We are planning to release this algorithm to the public in near future. Thank you for attention, and Let me know if you have any questions.